Hope you are seeing my screen now.
Yes, sir, it's visible.
So I just recall when I opened my old the previous QML presentation, that was 14th June. So exactly after 14 3 months we are starting our second the next cohorts. That's great. Consistent work, Sumit and team. I appreciate your efforts you are making for this cohort.
Thanks, KJ.
Okay, right. Move on to the topic. So QML, let's see, there is a few slides as a continuity for classical machine learning, but I'm not going to spend time here. Directly jumping into um, quantum machine learning. So before jumping into quantum machine learning, in general concept about machine learning is that some of the students or most of the students are thinking that machine learning is about Python programming. If you are thinking that way, please, my kind request, change that thought process. Machine learning is not about Python programming. Machine learning is about mathematical model. That mathematical model, one as a machine learning engineer, you have to learn the mathematical model. The implementation, you can choose Python or C, C++, Java, MATLAB or Julia, any language. So the machine learning is language agnostic. It is not Python programming. That is my kind request. With that request, let us move on to the quantum machine learning. So quantum machine learning is the intersection of machine learning, quantum computing, and then optimization technique. You might have figured out machine learning and then quantum computing, but the third component, optimization technique, is really a surprise for some of you. How optimization techniques come into picture? Not only for quantum machine learning, many of the quantum capabilities or quantum solutions, optimization is one of the main reason why we are selecting quantum computing. Now, with that as an introduction, I would like to show one short demo of quantum machine learning based solution. So, for which I will go here. Okay. Oh, not this one. Yeah. Um, I'm not going to run the program and then explain you, but I will show the result because some of you may be thinking that because before explaining the benefit or after seeing this benefit slide, let me see the benefit, then go there. What are the benefits of QML which is claimed by professionals who are entering the QML? It is speed, accuracy, security, scalability, and innovative approach. So speed and accuracy are important catalyst for pursuing QML for our AIML problem, right? So now, if you see this program, what I have opened now, this QSVM, Quantum Support Vector Machine. Why Quantum Support Vector Machine? See, I have Quantum Reservoir Computing also, but why I'm showing Quantum Support Vector Machine? Because Support Vector Machine in the classical world, very popular one, and then most of machine learning professionals or students who are learning machine learning, they know what is support vector machine. That is the reason why we have selected quantum support vector machine. And here what you are seeing is the classical support vector machine, which is imported from sklearn.support vector machine, and the famous iris dataset being used. We are reading the dataset and building the classical model. Here is the classical model. We are identifying the x data, meaning that the data and label. Then we are splitting train and test with 70-30 percentage. Then fitting with the training set and predicting with the test set, which will give you the confusion matrix and accuracy. Later, I want to analyze or I want to classify a new data, unseen data, I'm passing a new data here. So when I run this program, I'm getting this output. What is the output? The accuracy is 98 percentage, and this particular unseen data is classified as iris virginica, and this whole cell ran less than 1 second. Now this is the quantum part. You are seeing here I am creating the 4 objects like ZZ feature map, sampler, compute and compute fidelity. Using these things I am creating a feature map, then building the kernel. That kernel is passed to quantum support vector classifier, which is imported from qiskit underscore machine learning dot algorithm. Then this model, it is fitting the same way how the classical, we are fitting with the training and the training set, then predicting with the test set, which will give us the accuracy and confusion matrix. Then any number of time we can process unseen data. Here we are taking the same data. So this cell will run more than 30 seconds. You can literally, you have to wait, you have to see, it looks like a turn, and it is predicting wrongly. And actually the sample data what I have given is virginica, but it is predicting as versicolor. So what I'm showing now is the benefit what I'm claiming here, speed and accuracy both are not realized when we are building a quantum support vector machine problem with 150 subjects. And why so? Because I am running that program in my simulator with 32 GB RAM and everything classical. That is one main reason why we are getting less accuracy and speed. But if I run these things on a real QPU like IBM or Amazon Bracket or um, Google or Rigetti, those systems will give better accuracy and speed. So why I am showing this one, it is very, very important to understand the capability of simulator which is running in your laptop. And because most of you are going to build your proof of concept or prototyping using your laptop only, because you cannot buy a subscription from IBM or Amazon Bracket because they are very costly unless you have a paying customer or your organization is having a premium access, because they are taking care of the subscription cost. When you run those things in a classical system, you will disappointed by seeing the result. You should not get disappointed, that is natural. To show that only I have demonstrated this quantum support vector machine, but I have some other problem which are uh, um, quantum systems are outperforming classical. But in the interest of time, I'm moving to the next topic in the slide. Next one is challenges. Obviously QML, even though it is considered as the next big thing, it has its own challenges, because we are having the quantum systems in the nascent stage, and then we don't have a lot of qubits, and then they are Niskera systems. Beyond that, the knowledge gap, the talent gap, that is very huge. See, I'm a practicing data scientist. I'm in the data science since 2007 or 2008. That time it was not even named as a data science. That time it was called data analytics, where I started learning R programming. And 2016 onwards, I became a full-fledged data scientist. So I have a real good experience, and then I had an opportunity to work with a lot of bright minds in this field. But when I work with freshers who are coming from college, I'm seeing a lot of knowledge gap. So as a team, we have to do some, or how to say, the preparation. That is one important thing. The talent gap is one of the important challenge in the quantum machine learning. That is main reason most of them are coming with the Python programming mindset without the mathematical model as the foundation. Then comes, there is a comparison. It is a very lengthy, it is, I'm not going to discuss everything here. But the implementation part, you can see here quantum machine learning requires specialized quantum hardware. but this is a standard thing. And then practical applications like cryptography, optimization, those things. Then there are four approaches for building the quantum machine learning: classical data, classical data, classical algorithm, classical data, quantum data, classical algorithm, quantum data, quantum algorithm. Here, the quantum data, quantum algorithm is a ultimate approach, but here we don't have a quantum data input model. See, now only we are having few modules or few solutions for quantum sensing and metrology. So that quantum sensing is promising. You can collect the information as a quantum information, directly feed to quantum systems. That is going to give the real performance. But unfortunately, we are not having quantum sensing as a practical solution which is directly interfaced with the quantum systems, quantum computers. So this is the ultimate solution. But as of now, mostly classical data, quantum algorithm. How it is happening? We need to encode our classical data into quantum information. That is where these four methods of encoding: basis encoding, angle encoding, amplitude encoding, hybrid encoding. These four methods are used depending on your algorithm and use case and the nature of data. We will choose which is suitable for our problem at hand. I have prepared a table. This table will give you the right decision. So it is giving you the phase encoding or angle encoding suitable for quantum cryptography, quantum QFT, and it is also suitable for quantum machine learning. Amplitude encoding, this is the ideal approach for QML and simulation. And this density matrix or hybrid approach is not because that is a very costly affair, meaning that prepare your data set, we have to, or to do the encoding, we have to do a lot of computation. That's one reason density matrix encoding or hybrid encoding is not commonly utilized in the simple programs. But in my observation, some of the problems must be done with density matrix only. Then comes quantum information encoding, meaning that from where you can learn all those things, and then that encoding gives you these capabilities. Then what is the structure of a QML solution? A QML solution is always VQC. VQC means variational quantum circuit. The part of the VQC is PQC, which is parameterized quantum circuit. That's why I'm starting with the PQC. A PQC is a quantum system. 1 minute, sorry about it. I have to forgot to connect my charger. 1 minute.
Yeah, attendance link is shared and code is also shared in the chat. And Q&A is also open. You guys can type your questions because later we won't be able to take much questions. In Q&A, you can type your questions.
Yeah, I connected my charger. Okay, right. Sorry about that break because
Yeah.
I forgot that. So the PQC is a parameter circuit, a quantum circuit which will have a omega. This is not W, this is omega. Usually it is a theta. The theta will get changed depending on your outcome, and the outcome need to be compared with the previous iteration, then optimize it. That is where variational quantum circuit comes into picture. This is what the VQC, the variational circuit or the variational quantum circuit, which is the combination of your quantum circuit and this classical optimizer loss function. These are all classical model. So most of the quantum machine learning, not only quantum machine learning, even quantum optimization, most of the quantum solutions are VQC, variational quantum circuits. They will have a PQC, and a classical component. So this is the overall architecture of any QML program. Now, after hearing all those things, you will have some confusion. How this quantum support vector machine is performing that classification, right? Because if if you know the statistical aspect of support vector machine in classical world, you may recall that there is a hyperplane dividing your or classifying your data points, and from this hyperplane we have a positive offset and negative offset, which are called supports, and we will calculate the difference between the hyperplane and the support, the data points which are falling on the support line. That vector will give you the accuracy of the system. Based on that, we will um, uh, uh, classify your data points more accurately. That is the concept in classical world, and mathematically they are all processed with the help of a matrix or array concept. But when it comes to quantum computing, we are using this kind of approach, a data set which is pre-processed by encoding. If you remember the program I showed, that ZZ feature map, that is what that encoding or the data preparation you see here, that ZZ feature map, that is what the encoding feature map. Then there is a quantum kernel, and here you will see a kernel here, fidelity quantum kernel. So these are the components fed into your quantum support vector classifier, which is you can see here QSVC has a parameter. So this is a typical architecture of a kernel based estimation. How it is working: when I fed the feature map into the kernel, it will form an n-dimensional Hilbert space. So all of you, I believe, all of you remember that an n-dimensional Hilbert space can be visualized as a three-dimensional sphere with n or 2 power n possible states at the same time. They are forming a non-Euclidean space. Now, when you try to classify with a hyperplane, which is a straight line or linear line, but if this linear line is put on a non-Euclidean space, it will become a non-linear divider like this, or a classifier like this, a parabola. That is how a quantum support vector machine is classifying your data points. It is not the same way as classical. A quantum support vector machine is working entirely a different mathematical model. That is what you have to remember. That's why I included this visuals, which will help you to recall how this classification is happening in the quantum system. And this is the elevation. You can see here the feature map, original data set, but after the feature map, they are naturally getting divided easily. That's what I have for this session, and these are the books relevant to understand the mathematics. There is another personal preference, that is I have not included that one, but multiple times I'm told, but I'm not sure whether I have told you this batch. I recommend all of you to read this book, 17 equations. I will type in the chat window, okay? 17 equations that changed the world by Ion Stewart. This is the book I recommend to get the mathematical intuition of whatever you learn. Then if you read this one, it will be useful. Then these are all the various quantum machine learning books. My personal preference is Santanu Ganguly for the practical approach, and Maria Schuld book, followed by Peter Wittek book. These two things will give you a clear picture on quantum machine learning. I had a privilege of attending Professor Peter Wittek session, of course, in an online MOOC platform, but it was a amazing session where I learned quantum machine learning from this session. I think it is 2020 or 2021 that time. So this is a good source. We cannot skip it, and also